There you go. Matt, it's all yours.
Well, hi, everyone. Thanks for coming. And I'm really happy to introduce Paul Fleming, who's today's speaker at our seminar. Known Paul for quite a long time now. I think probably going back to when he was a PhD student at Vanderbilt, or maybe a postdoc working at Colorado in mines. But Paul is now a researcher at NREL and has expertise in wind farm control. And I would say over the past 10 years has been doing some of the most interesting work on offshore wind energy with in general with his work on wind farm control. And I've really just enjoyed his papers over the past 10 years and learned so much from them and been so impressed with the results. And so I'm delighted that he accepted our invitation to be a speaker today, and I'll let him take it from here.
Thank you very much, Matt. Nice introduction. And yeah, that's right. So I've been now at NREL. Let me make sure I'm actually controlling my slides. There we go. For maybe so maybe 12 years, or is that right? Yeah, 12 years at NREL, starting as a postdoc, and moving into research engineering position, and now PI for wind energy controls. And about the last 8 or 9 of that has been on this subject of wind farm control. And so when I was putting together this slide deck for today and thinking about this presentation, I thought it would be a nice way to introduce it would be to just kind of go chronological from where I started to where I am now. And hopefully you find some interest in it. So thanks a lot for joining. And feel free, I don't know how you guys normally do these seminars. I'm happy for questions whenever. So however you prefer to organize things. But you can also tell me I'm going too slow or something. So I start with single turbine control just briefly. So this is where I started working on, trying to develop new types of control of a single wind turbine. And these, your normal commercial scale utility wind turbine today has a number of active control loops. Some of them supervisory or, kind of low level, but at a high level of abstraction, you have a pitch control loop, which is regulating the rotor speed. You have a torque control loop, which is trying to balance the power generation and maximize power when the wind conditions aren't yet fully rated. And then you have a yaw control loop, which is basically trying to keep the turbine pointed in the wind. The turbine operates each of these control loops using onboard measurement systems. So to do the pitch control, it looks at measurements of its own rotor velocity. For the torque control, it's looking more or less, again, just at its own rotor velocity. And for the yaw control, there's a vane on top of the nacelle, which is sort of the feedback signal to the yaw controller. And its goals shown in this figure are really to maximize power when the wind speed isn't rated, and otherwise to keep the turbine safe through the minimization of loads. That's single turbine control. So what is wind farm control? So if we take this single turbine control, we can remap it to something like this. So you have a farm full of turbines, and every turbine is using its own measurements to satisfy objectives calibrated toward itself. So that's what we might see today. Single turbine control is a bunch of turbines controlling themselves using their own information for themselves. We might call a greedy approach. When we look at wind farm control, we sort of expand this matrix of possibilities. So on the right, you could say one way to do wind farm control would be not have the turbines communicate with each other, but have them pursue a globally optimal objective. So it might not be the case that what's optimal for one turbine is optimal at a farm level. On the bottom left, you could say you can keep the optimal objectives, but say that turbines have informations that other turbines might find useful in reaching their own objectives. That's another type of wind farm control. And then finally, in the bottom right is kind of our vision of the future, where there is both shared information between turbines and global objectives. And sharing information between turbines might look like, passing different meteorological information or current status, whereas like global loads might mean that the controls that lead to the optimal power production of one turbine aren't optimal on a farm level, and we'll get way into that. But yeah, you can say that wind farm control is the coordination of the control actions of individual turbines. Different objectives, different means, but maybe that's a nice catch-all. Why implement wind farm control? One main reason is to maximize energy production. So there's opportunities in this coordination to increase the overall energy production of a farm, which we'll talk about. There's also opportunities to reduce damage and increase lifetime of turbines. And finally, there's an opportunity to increase value of wind energy to the grid. The increased energy production that can come from better achievement of like yaw alignments, something we'll talk about later, or it could mean mitigation of wake losses. A recent paper, for instance, cited that offshore US farms might expect to lose 1/3 of their energy production on an annual basis to wakes. So there's a lot of upside to trying to reduce the amount of energy lost to wakes. Okay, so wind farm flow control then, when we add this flow into it, we're trying to further specify nomenclature-wise that we're trying to take control over the flow between turbines for some productive end. And this has been categorized in the past into axial induction control, shown on the left. These are figures from a colleague of mine at TU Delft, Jan Willem van Riggerden. In axial control, the concepts usually involve changing the amount of energy, axial induction control, excuse me, changing the value of energy captured upstream and redistributing some of that capture downstream, letting some of the flow pass through the first turbine to provide more energy to the second turbine. Another concept is called wake steering, where some axis is used and changed to redirect the direction the flow takes following the upstream turbine. So in this example, the turbine is yawed, the flow is steered away from a downstream turbine. These are the two broad classes, I would say, of wind farm flow control. If we think about wake redirection methods, zooming in here, this is where I personally have spent most of my time. This is trying to come up with a way to get the wake, this slow mass of flow behind a turbine after the energy is extracted, to not just necessarily propagate gently downstream if that's going right towards another turbine, but look at ways to have it go someplace else, or to change its properties into something better for the turbine following it. And so here we've looked in the past at using changes to the yaw angle, which is usually called wake steering, changing the tilt angle, and then trying to do something where you introduce an asymmetric moment into the flow using independent pitch control. Of these, really wake steering has proved to be the most promising and where I spent a lot of my time. And so when I got into wind farm control, this was the kind of state of the world that I was used to. There was these options and papers from a few other labs where they looked at a few of these things. And there's basically a tie between axial and wind farm and wake steering type controls, what was most beneficial. And what we in NREL started doing was simulating these things in higher fidelity models. This is an example of a simulation we did, looking at what if we just take one of these high fidelity large-eddy simulations that's doing computational fluid dynamics, embed turbines in the flow, and simulate different control conditions. We did this for axial control and for wake steering, and from our simulations, wake steering was the more promising. This is a simulation showing a line of turbines all aligned to the flow, and by implementing wake steering, yes, the first turbine is producing less power. So there's that like non-greedy approach, but the other four are making it up, such that the net difference in energy at the end of this simulation is a meaningful amount of increased production thanks to the application of wake steering. So I think, yeah, that was, I think, our early work, looking at LES and trying to identify which of these methods has potential. And that really led us towards wake steering. The next problem we had was, okay, so say you wanted to do this. You need to design a wind farm controller. What yaw angle should a turbine take in different operating conditions? And so that was really what led us to create what we called an engineering or control-oriented model of wake steering, which we named FLORIS. This is again a collaboration with TU Delft. So the idea with FLORIS was to build up models of wakes, but also wake steering, such that you could optimize out a wake steering controller and analyze its likely impact on a farm in a fast kind of analytic framework. So building this model was a lot of the important work of 5 to 8 years ago, and we basically continue to iterate it. It's finding more and more use these days. as just an open source framework for looking at wakes and wake steering. And we keep working on the underlying models and software engineering such that it can handle larger and larger farms, and looking at more and more algorithms for the design and robust analysis of wake steering controls. We also tried to contribute to and follow the literature of wake modeling. So when we started, really what was available in the analytic wake modeling framework for us to pick up was what's called the Jensen model. So this is a quote unquote top hat model of wakes, and you can see it on the left, where the wake is, following this expansion, but basically there's a hard line to where the wake is bounded in between. And there's no change in the depth of the wake as you move across the wake zone. At a different distance downstream, it's all the same. We found this was not workable for wake steering because it doesn't discuss the value of shifting the wake a little bit, moving the center depth of the wake to the side or left. So my colleague Peter Gebrat and I produced this multi-zone model of wake steering, which split the wake into 3 different zones: a near wake, a far wake, and a mid wake, that allowed more variation and much better predicted what would happen under wake steering. But more recently, work from EPFL in Switzerland, from Porticel's group and Majid Bastanka, produced a Gaussian model of wakes and wake steering, which was even more superior. It's now a continuous model, still analytically described, but also responsive to things like ambient turbulent levels in the flow. And then to that, in the far right, we added what we call the Gauss-Curl hybrid model of wakes, which also include lateral dislocations coming from vortices injected into the flow by wake steering. So this is the kind of progression we've been pursuing, this updating the model, designing new controllers, and then feeding back on each other as we go along. Doing this, we can now design controllers, or we could design controllers for a hypothetical farm that we would run in an LES, or Large-Eddy simulation, and then compare what FLORIS, our optimization tool, was expecting to gain out of these simulations and what we were observing in the simulation. So in this plot, you can see that the baseline expected average power production and the FLORIS optimized expected power production according to FLORIS, shown as solid dashed lines. If we look at the dynamic CFD simulation, we see that this is a fair approximation of what actually happens when we run the high fidelity models. Okay, so this process of iterating between our analytic design models and our higher fidelity simulation codes went on for a few years. But eventually we started having opportunities to try things in the field. And a nice early field test was took place at the site I work, used to be called the National Wind Technology Center. Now it's referred to as the Flatirons campus of NREL. But here, right here in Boulder, and you can see there we have some turbines in sight and a canyon there, El Dorado Canyon, producing a nice channel of rather intense winds through the winter up here on the mesa. So a good testing site. We placed a LiDAR on this 1.5 megawatt turbine on the right, where we have some ability to change the controls. And we also have this upstream Met tower we could use to look at the inflow conditions. So here's us working with the University of Stuttgart to add a LiDAR on the back of the nacelle, looking backwards, so scanning the wake of the turbine while we take it through various maneuvers. So it's a LiDAR that has a beam that's being reflected through 2 mirrors so that it can run a scanning pattern over the wake behind the turbine. So that's what you see here, this pattern. And it's a pulse LiDAR, so it can see 5 different distances at once. And like that, it is making this rosette pattern of scans. And then what we did is we overrode a little bit, or tricked the turbine into holding different yaw positions to see if the wake moved in the way we expected to from our analytic models and from our work with LES. And so we ran cases where we did scans. So each of these rows is a different yaw offset that we held, while each of the columns is a different distance downstream from the turbine. And what I'm showing here is where FLORIS expects the wakes to be in each of these scans. So as you kind of go from down the rows, you see the green circle is showing the FLORIS is expecting the wake to be inside this green circle. As the turbine yaws more and more, the wake should shift. And as you go downstream from left to right, the wake should continue to move over a bit. And that is not too far from what we observed looking at those LiDAR scans. So this was an early result, in the physical world, looking at wake steering. Another opportunity from this test was this turbine is highly instrumented with load sensing. So it gave us an opportunity to assess the impact of doing this yaw misalignment on the loads from the turbine. We could look at impact on blade, root bending, and tower bending, and different vibrations experienced along the shaft. And there's a pretty, thick paper on those results and an even thicker internal report. But I would say the key takeaway is you can design a region of operation of a reasonable amount of offsets happening in reasonable wind speeds where the impact on the loads is not too much. Okay. Following that test on one turbine, we were able to kind of graduate to doing tests on multiple turbines with turbines in their wake. So this gives us an opportunity to actually do wake steering for a benefit. So taking one turbine and having it do its wake steering to benefit another turbine. So this was a study we did in Colorado. It's a subset of a much larger farm where we looked at these turbines labeled T2 and T4 and designed using FLORIS optimal yaw offset angles for different wind directions and speeds, and looked at the impact we were having on this T3 in the middle. So when the winds were out of the north, we could run this north campaign with T2 as the controlled turbine, and with the winds out of the south, we could use T4. We basically run this experiment toggling every hour. So every hour we would either be in the baseline mode where the turbine was commanded to operate normally, or we'd be in the controlled mode where it was given this optimal yaw offset. And one thing we found trying to do this now instead of holding like the fixed offset like we did on our single turbine is you have more control problems here. So if you look at this figure on the right, the black line is showing the yaw offset we were trying to achieve for different wind directions, and then the green dots are showing what we actually achieved. The yaw controls of wind turbines are slow. The turbines yaw at less than 1 degree per second, and they don't yaw all the time. It's more or less a bang-bang controller. And so precisely following an offset is difficult, and it raised to our attention that, while the early work was focused, I think, a lot on wake modeling and modeling these control features in the flow, the work of the future is really going to be on the design of the controllers in a dynamic way. How should they operate to best achieve what they're trying to achieve? But here's an example. This is basically the energy production of this third turbine as we kind of went along, where the blue line is the energy production relative to an unwaked turbine for the different degrees in the x-axis when the upstream turbine operates normally, whereas the green line when the upstream turbine is doing wake steering. So here you get a nice view of, as the data comes in, we have our confidence interval shrinking and the pattern of, that area where we are operating wake steering, from just around the magenta dash line where the turbine is directly upstream from the other, and the, and off to the right. So in between the magenta bands is where we were actively trying to do wake steering. You see those two lines come apart in a good way. And you see a gain in the energy production downstream. And we could compare these results with what we were expecting from FLORIS. So in these figure, we have the banded lines, the blue and magenta are the baseline and controlled field results for energy production. And then the dashed lines are the expectations from FLORIS. Published these in 2 open journals. Since this test, we completed a few additional tests with other partners. So with the wind farms developers, ENGIE and RES, similar tests, but each one has like slightly different wrinkles in how things were implemented and what controls were applied. But again, a lot of learning able to take place by testing things over and over. So this last paper is only from, I would say, like work done within the last year or two. And so really bringing us now up to pretty close to where I spend a lot of my time now, which is, setting up more and more control experiments for different sites and thinking about how to better and better implement the controls themselves, and that sort of thing. We'll talk a little bit more about that. But first, I'd like to do a short pivot, because you'll realize now that all the cases we talked about so far of onshore sites. But in point of fact, wake steering seems a little bit more suitable to offshore sites for a few reasons. One, the offshore conditions are less turbulent, meaning wake losses are expected to be more intense. And also there's a lot of stakeholder consideration drive offshore sites to be fairly gridded, meaning you get long lines of turbines in a row producing wake patterns, whereas onshore you have more freedom to design irregular farms that can minimize wake effects just by spacing turbines out or putting turbines on ridges, things that aren't necessarily available offshore. And so one of my main projects now is looking at the value of wind farm control for different US offshore locations. So, the first sites for US offshore, the first US offshore farm was off Rhode Island, but there's a lot coming to the US Eastern Seaboard, and plans also for the California coast and Hawaii and Great Lakes. And so we're trying to do some projects now with it's called the NOWRDC, it's a consortium project with NYSERDA on looking at the value of wake steering for US offshore farms. And this, I think, is an interesting work. The other thing that I'm working on these days is leading IEA Wind tasks. So IEA Wind collaborates big international research efforts across different activities into tasks. And so task 44 is a new task, which is looking to organize research in the area of wind farm control between research institutes like NREL and universities, and then also developers that implement this in the sites, and OEMs or turbine manufacturers and consultants who are coming up with commercial versions of wind farm controls. Okay, so with that said, just like to do one more digression into the other type of wind farm control, and then I'll wrap it up. What I've been talking about is what we usually call wind farm flow control, methods that seek to impact the flow for the benefit of the farm. But the other thing we talked about was sharing information. And this is another control idea coming out of NREL. This comes from my colleague, Jen King. And so we start by considering this is real SCADA data from a farm, the direction the turbines are pointing over time in this particular case. And here you see that the turbines, if you've ever driven past a farm in real life, you usually find one turbine in the mix that's pointed in a kind of impossible direction. It can't be right, given the way other turbines are pointing. And it has to do with the fact that it only has typically this one sensor on its own nacelle, and it has some difficult decisions to make. If the wind veers to the left, should it chase it, or should it wait a little bit to see if it comes back? Or maybe it chases it and then it does veer back, and now it's stuck because it has a timer that says it can't yaw 30 seconds after it just finished yaw, et cetera, et cetera, et cetera. So you get a lot of situations where turbine orientations don't make a lot of sense in the full context and are probably wrong. And so what consensus control is looking to do is share information between turbines to come up with a more spatially reasonable estimate of the wind direction flow and what it's likely to be in the near future. And the word consensus reflects the fact that this is a consensus type of optimization, saying you're trying to design trying to make a map of wind directions that minimizes the error between each turbine's measurement and the local consensus direction, but also the error to all of the neighbors, saying that a direction at a turbine should make sense given the turbine's measurement, but also should make sense based on the closest neighbors. And you do a consensus optimization to realize that. When you do that, you get something like this comparison. So on the left is what actually occurs in terms of looking at the time history. So there's this event coming through where the wind direction is changing, and different turbines are realizing this at different moments, and there's sort of an idiosyncratic change in direction as each turbine individually takes advantage of the moment to change directions. Whereas on the right, you can see that this can be coordinated with the turbine share information, and turbines that sort of get stuck backwards can get more quickly aligned. Turbines that have clearly faulty sensors, there's this red one. Oh, it's gone now. Anyway, this turbines that just really are clearly experiencing a problem that can lean on their neighbors. So this is something we would call consensus. We've done some hybrid analysis to show that consensus can, without changing the objective, so it's not wake steering, the objective of each turbine is still as it was, stay aligned to the flow. But by sharing information, turbines and their slow controllers are just much better able to do that. And this is one study we did showing that there's an opportunity for another increase in power production when you apply such a method. So that, I think, is my talk on wind farm controls. So I think most farms today operate in this top left box still, where the dominant operational control is turbines using their own in-house information to achieve their own objectives. We have separate projects looking at this top right box, where turbines using their own information, but trying to pursue wake control strategies that will benefit their neighbors, or the bottom left box, keeping their same objectives, but sharing information. And in the next year or so, we'll start testing basically the combination of both sharing information and trying to implement things like wake steering and wake control to get the best possible energy production out of the farm. And yeah, with that, thank you for joining me, and happy to talk some more if anyone's interested. Or yeah, thank you.
Thank you, Paul. So I think you can stop sharing your screen and we can go everybody can turn on their cameras and we can go to the Q&A session.
I can ask a question. Yeah, thank you so much for the talk. It's really interesting seeing the progression of this side of things. I was wondering kind of generally about the wake steering controls. Like, how are the controls expected to, are the control systems expected to have to change significantly between turbines? Like, will one GE turbine have to have significantly different control scheme than another?
I think that, like, on the one hand, no, you can work with anything. But the big dream is really to try to, so like right now, if we look at a controller, we kind of look at the turbines, yaw controller as it is now, and figure out how to get it to do what we want, but that's not really optimal. The optimal thing would be a replacement and letting the turbine controller be best suited to the wind farm objectives. But that's not an easy thing to do. There's a lot of industrial turbine controllers have a lot of safety checks built into them, and they don't change anything lightly. And so that's not how we've done it to date. But I think as you see more and more turbine manufacturers themselves offering products related to wake steering, wind farm control, they obviously have the ability to tailor things. So I think there you will see more and more optimization of the turbine controller to match the wind farm controller.
Hey, Paul, very great presentation, very interesting. I was wondering if you could show the slide with the loading again.
Like the impact on turbine loads?
Yeah, there was a region where you're pointing to that you said it reduced loads in that region, like region 2. What region was that exactly?
Let me have a look. Sorry. Can you see my slides again?
No, not yet.
Oh, sorry. Oh, coming up. Okay. You mean this slide?
Yeah.
Sorry. Yeah, some jargon in this slide. So region 2 is the below rated region. If you look at sort of a canonical like turbine control, like wind speed on the x-axis, region 2 is where there isn't enough wind energy to fully rate the turbine, And so the turbine operates in this sort of variable speed mode and tries to get the most power out. The reason we specify region 2 is that actually you don't do wake steering too much in region 3, because at a certain point there are no wake losses anymore. Even considering wakes, all the turbines are fully rated, and so there's nothing left to do. So this slide is just one of the reasons the loads impact. I think when people first hear of this like concept, the first time they hear of wake steering, there's an assumption that the loads impact should be pretty large. And one of the things to stress is that wake steering is only done for certain wind directions, but also only for certain wind speeds. For a lot of the higher wind speeds where some of the bigger loads will be, you don't actually do wake steering because there would be no point.
Does that mean wake steering only would be used in region 2, or like lower end of region 3 too as well?
Exactly, yeah. Unless you were doing it specifically for loads. So unless so I hear we're probably getting into more like topics of research now. So there's papers where you could say you could do wake steering because you want to move a wake off a downstream turbine, because partial wakes are load intensive. You're doing wake steering for loads. That would give you a reason to do it in region 3. But typically, once every turbine on the farm is fully rated, at least from an energy perspective, there's no advantage anymore, because any additional energy you send downstream, the pitch controller is just going to dump. So, that's why we typically don't operate. And then it just makes it a little bit easier to, make the loads case. Like if you're not operating in really, really windy conditions, you don't have to consider what the loads impacts would be under those conditions. Okay. Thank you.
Oh, I think there's a question in the chat too.
Oh, okay. Now let's see. Right. Yes, okay, thanks. So the Gaussian method is describing the underlying base wake, and it's derived in a series of 3 papers from Portagel and his students, and especially Majid Basanka, who's now a professor at University of Durham. And so they describe, using a RANS budget method, the wake and a method for wake deflection. We after implementing that model, we came up with another model called the curl model, which is describing wake deflection, not wakes, but wake deflection, as being driven by a pair of counter-rotating vortices. So these, it's like if you imagine a misaligned rotor from the flow, there's a lift component now, and so there should be these and indeed you see them in the LES simulations. There's 2 counter-rotating vortices come off. They curl the wake, so the wake of a wind turbine doing wake steering starts to look rather kidney beanish. And they also, we say, are responsible for the deflection. That would be just kind of a point of trivia, I guess. But one of the things about them is that they persist. And so what we wanted to reflect when we introduced the gas curl wake model is that if a turbine upstream of like 2 other turbines does wake steering, the first one will generate these cross flows, and it will be as though the second turbine is also wake steering, even if it's not, because those vortices will persist through the second turbine. We call this secondary steering. So saying that once one upstream turbine starts to do wake steering, there will be structures in the flow that are going to persist regardless of what other turbines do that could affect a type of steering on future turbines. And that's what we did with the Gauss-Curl hybrid model. We kept the Gaussian wake model, but applied these analytic expressions of these counter-rotating vortices to better explain some of the physical phenomenon once you start doing wake steering. Thanks for the question.
Could I ask about the last control scheme you mentioned, the consensus control?
Yeah, sure.
Did you only look into that for like yaw alignment purposes? Is that the main goal or the main kind of target of that control?
Originally, yes. A lot of these things kind of take on more uses once you start to use them. So I think the original purpose was let's better align turbines to the flow and provide some anticipatory capabilities. So like the canonical problem is like a turbine is sitting in the stream, the wind direction changes 20 degrees, and it will take like 20-30 seconds for it to also yaw 20 degrees. Should it start now or should it wait? And the typical way to do this is just apply a pretty long filter and say, if the wind direction is 10 degrees away for 20 seconds, then yes, I'll yaw. Or, something, there's usually some sort of dead band, some sort of filter. This is replacing that with a logic that says, if me and my neighbors all see the same direction change, I'm going to start right now. And so that was the original intention. Since then, we found other applications for it. So one thing is it provides a better input to the wake steering model. So trying to decide where the wake is likely to go is better predicted, we think, by the consensus of a few turbines versus one local measurement. And then now I think it would be more used for things like nowcasting the available power. So trying to describe if you're doing some form of grid interaction where you're holding in reserve some energy production for the grid, consensus gives you a useful input for estimating how much power you could be making if you were going all out. And also, if your farm is large enough, it might give you like some ability to do some sort of very short timescale preview. So this will be more about like supporting the grid in balancing the local area or just like production and load. So, increasing number of use cases, I think. We've also found it's useful, like we have some tests running now. Once you start doing it, it also gives you a way to kind of highlight probable sensor miscalibrations. So if one turbine is always out from its neighbors, that probably maybe just want to go send a technician there. So stuff like that. I think our experience is a lot of these things end up having more use cases once you start applying them.
That's really interesting. Thank you.
No problem. Okay.
So there's another question in the chat box.
Yeah, I think so. I think yes. It's complicated because there's a little bit. So we're like a federal laboratory, so we're publicly funded. So everything we do goes into the public, but commercial companies kind of have reversed incentives. And so we don't get very detailed descriptions of what they're doing internally. But we expect, based on like the conversation we do have, most companies are using FLORIS at least a little bit. Maybe they're using it to design their own in-house versions of things. It is open source with an Apache license, so you can take it and modify it, or you can just take bits of the code out, So somewhere, some companies I think are using it more or less directly. Some companies just, another model they can check against. Some companies, so depending on the company, but yeah, I think so. We've had a few former postdocs leave and join some of these companies to work with them on their wind farm controllers. So those are the ones I really expect are FLORIS heavy. But I think so. But not too many people come out and say it.
I have another question on cost. So obviously with this wind farm control, you add a bunch of complexity to, the whole wind farm. I was wondering, like, how does the increase in complexity and cost compare to, the net increase in annual production? Is there a large margin, or is the benefit marginal?
Yeah, it's a good question. I think that's one where we try to work mostly with either there's a systems engineering group at NREL that does a little bit more of this like holistic cost versus increased revenue, or we work with companies on questions like that. Yeah, to my perspective, it's a good trade because there's no new equipment. So like, take for example, like an alternative, like adding LiDARs to every turbine. There's a very clear, like, this thing wasn't there and now it's there. So you have to pay for it. You have to pay to maintain it. A lot of the wind farms, modern wind farms, for example, already have some degree of communication. There is a central like control center. It wasn't helping with the yaw control, but you don't need to lay new fiber or something to add the functionality. It can be more or less a software change, depending on how modern the farm is. Obviously, some places would need a pretty big retrofit. And then some places it's not a retrofit at all. So for instance, Siemens Gamesa offers Wake Adapt. So this is basically a wake steering product that you can buy when you install the turbine. So there's no retrofit like at all in that case. So then I think the logic is really easy, just comes pre-installed. And so it probably depends. I would guess, what we say is when we look at things, the first indicator of the value of wake steering to a farm is the annual wake losses. You can make a farm, you imagine like a farm on a ridge line perpendicular to the main flow direction. They might have very little wake losses, which means they have very little to gain from wake loss reduction strategies. You take other places like Lilligren, like an offshore farm with 3 diameter spacing and 40% annual wake losses, something like that. A very high case, no matter what you do. It'd be very easy to recoup. So I think those are like the kind of the strategies, but yeah, it depends. And I think the loading impact is probably one of the more like urgent questions. Like if it's going to lead to like a bit more downtime or increased number of replacements, that obviously is going to shoot everything in the foot real quick. And so that a lot of research goes into how do we do this so that it doesn't negatively affect wakes. I think that's a really tough question because this series of really nice papers from someone from ECNTNO called Stoyan Kanov, where he looks and says, sometimes a turbine is upstream doing this yaw misalignment and having a little bit of an increase in loads. Sometimes it's downstream having a wake pushed off it and having its loads decreased. And then when you look across the year, if it balances out, he finds most of the loads decrease a little bit. But this is really complicated, and it gets down really into the weeds, like how well balanced is the rotor. Some turbines will suffer more or less from being misaligned and things. So a lot to think about in that within that question. And
that's a good point. I didn't think about reduction in maintenance costs could help, but it also sounds like the software is just, you say it's already there, the system's already there, just writing some code to update it. So the cost is probably much more minimal than So
yeah,
okay,
that will really depend on the farm. So like I said, like a farm installed 10, 20 years ago, that's really not true. You'd have to retrofit. The thing is, a lot of farms are retrofitting anyway. This whole businesses whose business model is retrofitting turbine controllers right now without doing wake steering. They just say, we've just learned a lot about how to do wind turbine controls since the 90s. So just replace the controller with this like hardware unit. And it is expensive, but it pays for itself in terms of like better energy production and reduced fatigue problems. Like you can do things like, I don't know, like adding like damping signals to some of the key loads or something. So because that's already a business model, you can see like this, like a company like Windesco offering like a retrofit that includes wake steering or consensus like controls and things like that. So yeah, I think the cost benefit will not be the same for every farm, and there will be farms where it doesn't clear it, and there'll be farms where it's a slam dunk, would be my guess. So
thank you.
No problem. Very true. Yeah. So you can see his website, and you can see this kind of a pitch being made to wind farm owners to upgrade their control systems to what you call like an aftermarket control product that they build and install.
I didn't
I'll try to
realize.
sneak in a quick question here and then mute myself again quickly. And
Sure.
sorry, I had to run out. So you may have addressed this, but one thing that always, to me, seems so challenging with wind farm control and why it's such an interesting research question is the time lag between changes in turbine conditions and the net effect of the change in the turbine conditions laid on top of the noise in the signal. And so, yeah, again, forgive me if you actually directly address this, but anyway, I'm just gonna ask, which is like, how hard is it sometimes to tell if what you're doing is improving performance or if the conditions have changed, or like, how do you extract the signal to noise in such like with such enormous time lags of what I have to assume are, hundreds of seconds between, say, changing the yaw to turbine and then seeing the net effect downstream?
Oh yeah, that's a good question. So I would say if you take any particular 10 to 20 minute time series, you can't. It's ambiguous. You have to build up statistics over a month or more. That is my impression. That is
Over
exactly
months, you said.
Yeah. So
Wow,
that
okay.
one figure I showed one figure where we were making the energy graph over time. It took about 2 weeks to come into view, but it significantly changed over the course of 3-4 months until around 2 months in, it's kind of locked into what it's going to be.
Got it.
And this has to do with like. This is a problem, I think, for all. Any toggle testing you do at a wind farm, ideally you do it for a year because the results won't be the same in the summer and the winter. And it's just a fact.
Stability and seasonal effects and all of that, yeah.
Yeah, and so it's just a problem. But yeah, we're exposed to that in a special way because you need a few repeated observations of similar conditions before you can say much of anything. I think
it's such an interesting problem. Like, to know if your algorithm works requires like 2 side-by-side years of data. Like, it's just sort of an enormously, I guess, noisy signal, I suppose, is the issue.
It's very noisy. The result is very dependent on the wind direction, and so, but it creates its own interesting research problem. So actually, with this release of FLORIS v3, we're releasing a new tool we call Flask, which is our toolbox for how we do these comparisons.
Oh, wow.
So we've used bootstrapping and things like that to try to make some assessment, to try to make some statistical assessments over like without assuming a distribution and things like that. And other people have monkeyed around with like fitting machine learning type things to the positive and negative case and trying. It's a good question, and it's actually when we talk to industry, it's the one we get the most often. I think like the theory of wake steering, like at some point people agree with that, but like the real question is like what we do now. We take one turbine, we don't change it, and we change these ones, and we compare back to this one. That's pretty effective because you can look at this nearby turbine, you can compare the power production, and you don't need to know the wind speed and direction too much because you have this other turbine, or even better, a few other turbines standing in as the hypothetical of what that turbine would have been doing under the control case. But when you apply wind farm control to the whole farm, I think everyone's a little bit scratching their heads. How will you know what the counterfactual would have been? And
could you apply it to half the farm where the line is half based on the wind direction?
Yeah, so that's what we do. So like we have some bigger tests coming in for like the Midwest and they'll still be toggle tested, but one day they won't be toggle tested, right? That's the main thing.
Oh,
so
I see. Okay.
Once you stop doing that, because like someday it won't be research. You'll just like you'll pay your OEM for their wake steering product, or you'll pay your consultancy, and they won't run a toggle test because it's a thing you bought and now it's on. But it does present a little bit of a conundrum. Or maybe you'll always have to toggle test to prove yourself it's working, and then you'll stop toggle testing.
I guess what I was saying was, say the wind's coming from the north, if you toggled on the east but not the west half of the farm, like over the course of a day, can you then at least get?
Yes, that is the plan right now.
That's the plan. Oh, I see. Okay.
Yeah. So right now we more or less toggle in time, but there are plans to do like an AT-BT test. Yeah. And I think those all provide, and maybe both, or there's lots of interesting design of experiment questions in there. And here I kind of hope we're doing some spade work for things not related to wind farm control. Just how do you tell if you change anything about a wind farm? You know, how do you quickly kind of suss out the impact, assuming, because yeah, maybe you and I are diving into the weeds. DNV will say you should do it for a year, you know, and then you never get a year because practical things come up, et cetera, et cetera. So fast ways to observe small changes in highly noisy systems like wind farms. Interesting research question, I think, and something like a mathematician could really dig his teeth into. Anyway.
Yeah, for sure. Thanks. I need to mute myself now. I'll let others people ask questions.
Gotcha.
How long are the tests that you're planning in these Midwest farms?
Multi-year tests.
Oh, wow.
That is always a dream. The practical things come up though. Turbines go down for unrelated reasons, or it takes longer than you think to get the contracting done. Like, yeah, it's all like it's just a lot of complicating things. I think anyone doing field experiments in any field is just aware of the reality that you hope to get all this data, and you in practice can get a lot less. So, and it's not, I don't think we're special in this regard at all. When I read wind farm control studies from other centers, there's always this paragraph saying we wish we had collected more data, but we ran out of time. And I think so with that said, and I think there's just a general desire to be able to test things quickly, because running a test for a year can be expensive if you're a company and you have to put manpower on this test, and you have to, you know, if you're running a test that's possibly losing energy, you have to consider that a cost and stuff. So that's why, you know, we've put a lot of thought into our methods of comparing, you know, the A and B cases of our toggle tests and trying to establish a way to do statistics over them. Yeah, so it's a really good question.
I think if we don't have more questions, I just want to say thank you, Paul Fleming, for being with us. And,
Hey, you're welcome.
And we look forward to have those next findings of your research. I would like to use this last minutes to share the links is on the Q&A box for our next seminar. Greg Nemeth from the University of Wisconsin will be with us talking about dynamic industrial policy for climate change.